Welcome to a lesson with Dr. Powell. Let's talk about how derivatives can be viewed or thought of in terms of projections and similar triangles. For instance, suppose I have a function here, and if it's smooth up close, that function looks like a straight line. And let's suppose in this case, this happens at an x value like 3. Suppose the slope of this line is 2. In particular, if I have a run of 1, I'm going to have a rise of plus 2. Now, in general, we can think of the derivative. Okay, so what is the derivative? We could think of it as the slope of this tangent line. But the slope of this tangent line is also kind of like a function, if you will, that goes from run to rise. And this is a very important analogy because as we extend what we mean by derivative, we're going to have to use this, especially if we go into more dimensions. It's not going to just be just a single number that we get for the derivative, but it's going to be kind of a function that represents this idea where you input run and you output rise. I'm going to give the slope or the derivative. It has lots of different notations. I mean, one common notation is just say f prime of 3. But for this particular circumstance, I'll use a different notation. So the derivative I'm going to notate by capital D f. And if I want to be fancy, I'll say at x equals 3. So at a particular input value, it's going to represent this function. This function will change per input value. So at x equals 3, I know the slope is 2. So for instance, if I input a run of 1, the rise will be the output of this we'll get a rise of 2. I can change this up a little bit. What if I input a run of 4? And particularly, this is the slope of the tangent line, right? So even though the line is off the curve, that's okay, because this really is referring to the tangent line itself. This is the run on the tangent line. This is the rise on the tangent line. So given a run of 4 on the tangent line, what would the rise be? Well, it would be 8, and you could check. 8 divided by 4 is 2, and that's exactly what we have for the slope. So thought of this way, this is it's like a function. Now, in particular, what if we were to plug in just an arbitrary h? Okay, what if our run was h? What would our rise be? Well, it would have to be 2h, because we want 2 over h, or 2h over h to be equal to 2, rise over run. So in that sense, we have that nice function in terms of that goes from run to rise. And it's just simply multiplication here by the constant slope. I mean, nothing real fancy. And that's why we haven't mentioned it before, because this would be really silly if that's all we were thinking about. However, we need to look at it this way. As we go into higher dimensions, we need to be thinking of the derivative as not just simply a number, but as kind of this run to rise type function that's located only at a specific single point. Now, how can we get this constant? This is also something interesting that we will be generalizing. Here, if we take the run and we go from this starting point on the function to this one, where we kind of represents the run of 1 on the tangent line, then if we take this and we project it onto the line that's parallel to the y-axis, where the y-axis represents output of the function, notice the projection here is precisely this 2, the slope. So for a run of 1, just take the projection onto that line that represents output and where our output values, and you get the slope. So you can think of this too in a couple different ways. You could think of it as slope itself, or you could just think of it as projection of the line that's approximating the function. onto the line that represents output for a run of 1. So specifically, a run of 1 will give you that actual slope. So you can think of that too as a projection. Thanks for watching.